Hey friends, welcome to the next session. 20 questions. Topic is serving tier decisions, parent-child retrieval architecture, and AI search vector normalization. Each question gets read out, then a 10-second countdown before the reveal. Let's roll. Here we go. Question 1. Find what the distractors miss. A generative AI engineer at Aldgate Systems is configuring a feature-serving endpoint that supplies real-time context to a credit risk LLM application. The endpoint must retrieve a customer's pre-materialized account tier and recent transaction history from a feature table, and also compute a derived creditworthiness score on demand by applying a business logic transformation to those retrieved values. Which two FeatureSpec components are required to implement both capabilities? Select 2. Review the answer choices on screen. The correct answers are option A and option C. 3 plausible component names that simply do not exist. A feature spec supports 2 component types that address the 2 distinct requirements here. Feature lookup retrieves specific columns from a pre-materialized feature table using a primary key, which is exactly how account tier and transaction history stored in a feature table are accessed at inference time. Feature function applies a Python function on demand at serving time, producing derived values, such as a creditworthiness score computed from the looked-up inputs, that are calculated fresh for each request rather than stored in advance. Feature pipeline is not a component of feature spec. The coordination between lookups and functions is handled implicitly by the feature spec definition itself. Feature group is not a recognized feature spec component. Bundling related features is achieved by including multiple feature lookup entries within the same spec. Feature scheduler does not exist as a feature spec component. Periodic recomputation of materialized features is managed through separate scheduled pipeline runs outside the serving endpoint. Next up, question 2. Separate context from noise. A generative AI engineer at a large retail company is building a product recommendation search system backed by Databricks AI Search. The product catalog contains 1.8 billion items, each represented by a 768-dimension embedding. During peak catalog refresh windows, indexing new and updated product records is slow and causes latency spikes in search results. Which AI search endpoint configuration should the engineer select to address both the scale and indexing performance requirements? Select 1. Review the answer choices on screen. The correct answer is option D. Scale numbers eliminate 3 of 4 options immediately. A storage-optimized endpoint is specifically designed for vector stores exceeding 1 billion items and delivers 10 to 20 times faster indexing compared to standard endpoints, directly addressing both the scale challenge of 1.8 billion items and the indexing performance degradation during peak refresh windows. Standard endpoints support approximately 320 million vectors at 768 dimensions, well below the 1.8 billion item requirement, so adding replicas does not overcome the per-endpoint capacity ceiling. Pre-filtering reduces the number of vectors evaluated at query time, but does nothing to accelerate the indexing pipeline that processes new and updated catalog records. Sharding across multiple standard endpoints introduces significant operational complexity, requires custom routing logic, and still cannot address the per-endpoint capacity limitation that makes the standard tier unsuitable for this scale. The scale numbers here are the whole story. Let me put them on screen for you. Picture a product catalog with 1.8 billion items. Each item has a 768 number vector, a list of numbers your AI uses to find similar products. Now try to put that in a standard Databricks AI search endpoint. You can't. Standard endpoints max out at roughly 320 million vectors at that size. That is barely 18% of your catalog. Adding replicas does not help. Replicas copy the load, not the capacity, Storage-optimized endpoints raise the ceiling to 1 billion vectors. They also index 10 to 20 times faster than standard endpoints. During peak catalog refresh windows, that means minutes instead of hours. The bars show it clearly. Standard falls way short. Storage-optimized is the only endpoint type built for this scale. Next up, question 3. Compare scope and condition. A generative AI engineer is designing a feature-serving endpoint for a real-time loan risk assessment application. Each request must retrieve a borrower's pre-materialized credit history features from an online feature table and apply a dynamic debt-to-income ratio calculation using values present in the request payload. Which two components must be included in the feature spec definition to satisfy both requirements? Select 2. Review the answer choices on screen. The correct answers are option A and option C. Same two correct answers, different distractor names to spot. Feature lookup retrieves one or more pre-materialized columns from an online feature table using a primary key lookup, which is the correct component for fetching stored credit history features. Feature function applies a Python or SQL transformation to values available at request time, making it the correct component for computing on-demand derived features such as the debt-to-income ratio. Feature index is not a valid feature spec component. Index structures within AI search are separate from feature-serving configurations. Feature cache is not a component in the Databricks Feature Serving API. Endpoint-level caching behavior is managed transparently by the platform infrastructure. Feature embedding is not a feature spec component. Embedding generation is handled by separate model endpoints and is not part of the feature-serving pipeline. Now, question 4. Translate the story into requirements. A generative AI engineer at Talbot AI is comparing two prompt templates for a customer support chatbot. Template precision uses highly structured step-by-step instructions, while template concise uses brief natural language directives. When each template's responses are scored independently, both consistently receive near-perfect scores, making it impossible to differentiate their quality from aggregate averages alone. Which LLM-as-judge methodology should the engineer use to reliably determine which template produces better responses? Select 1. Review the answer choices on screen. The correct answer is option C. Score compression at the top reveals a methodology blind spot. Pairwise comparison is purpose-built for directly contrasting two candidate outputs. By presenting the query and both responses to the judge simultaneously and asking it to select the better one, this methodology captures relative quality differences and produces judgments that align more closely with human preference than independent scoring does. Single output scoring evaluates each response in isolation, which introduces inter-run variance and score compression near the top of the scale. When two templates produce similarly strong responses, these aggregate averages often fail to discriminate between them reliably. Retrieval groundedness measures whether a response is supported by retrieved context and is a RAG faithfulness metric, not a mechanism for comparing prompt template quality. G-eval with chain of thought is a single output technique in which the judge reasons step by step before assigning a score to one response. It is not designed for head-to-head comparison of two candidates and shares the same instability drawbacks as other pointwise scoring methods. Let us keep moving. Question 5. Watch the tempting shortcut. A generative AI engineer at Litware Financial has a production LLM endpoint serving 32,000 queries per second with stable, predictable daily traffic. The team currently uses pay-per-token pricing and observes unpredictable monthly billing spikes. They need cost predictability and the lowest per-request overhead for sustained high-throughput production use. Which deployment configuration should they adopt? Select 1. Review the answer choices on screen. The correct answer is option B. Pay per token carries no latency SLA guarantee at volume. Provisioned throughput is the recommended deployment mode for all production workloads, particularly at high query volumes. It guarantees a minimum throughput level in tokens per second, delivers overhead latency under 50 milliseconds at over 25,000 queries per second, and converts variable billing into a predictable capacity cost. Pay-per-token pricing is recommended only during early development and exploration phases before stable traffic patterns are established, and enabling auto-scaling on a pay-per-token endpoint does not address cost predictability. Adding more pay-per-token endpoints still results in variable costs proportional to usage while adding load balancer management overhead. Reducing context window size alters application behavior and may degrade answer quality without addressing the underlying billing unpredictability. FeatureSpec recognizes only feature lookup and feature function. Reject every other named component. Storage-optimized AI search handles billion-plus vector catalogs. When absolute LLM-judge scores converge, pairwise comparison is the diagnostic escape hatch. Let us keep moving. Question 6. Check whether it asks what or why. A generative AI engineer at Cloverdale Healthcare has deployed a RAG application that answers clinical queries by retrieving passages from medical guidelines. The compliance team is concerned the LLM may be introducing clinical claims not present in the retrieved guideline text. Which MLflow built-in scorer should the engineer use to detect this behavior? Select one. Review the answer choices on screen. The correct answer is option A. Clinical hallucination is a grounding failure, not a relevance one. Faithfulness is specifically designed to measure how factually consistent a generated output is with the provided context. A high faithfulness score means the answer stays within information present in the retrieved medical guidelines, while a low score signals the model may be contradicting or ignoring the context and introducing content not grounded in the source, exactly the compliance concern the team needs to monitor. Answer_relevance evaluates whether the output is topically appropriate to the input question, but explicitly ignores context, so it cannot detect when an answer introduces hallucinated clinical information absent from the retrieved guidelines. Answer_similarity compares the generated output against a labeled ground truth reference answer, which the team does not have for every clinical query. Answer_correctness also requires labeled ground truth answers to measure factual accuracy, and is therefore unsuitable when the only available reference material is the retrieved guideline text itself. Let us keep moving. Question 7. One detail changes the answer. A generative AI engineer at Glencoe AI has enabled inference tables on a deployed model serving endpoint and is building an observability dashboard. While reviewing the captured data, they notice certain requests are missing from the table entirely. They want to understand which HTTP status codes correspond to requests that inference tables may not log. Which set of status codes does this describe? Select one. Review the answer choices on screen. The correct answer is option B. 4 specific codes that can vanish from your observability layer. Requests returning HTTP status codes 401, unauthorized, 403, forbidden, 429, rate limit exceeded, and 500, internal server error, may not be captured in inference tables. These error responses typically occur as a result of authentication failures, permission denials, throttling events, or internal processing failures that can prevent the logging mechanism from completing the write operation successfully. Successful 200 series responses are the primary targets of inference table logging and are consistently captured as long as the payload falls within the 10 MB size limit. Client error codes such as 400, 404, 408, and 422 represent request validation or routing failures and are generally logged when they occur. Redirect codes in the 300 series are not applicable to model serving endpoints, which do not issue HTTP redirects in normal REST API operation. Let's slow down here. Inference tables have a logging blind spot this question is testing. Imagine you deploy a model and wire up inference tables to watch every request. One morning you spot gaps, 12 requests just aren't there. Here's why. These tables are best effort. 4 HTTP codes can fall through the cracks. Code 401 means a bad API key. Code 403 means wrong permissions. Code 429 means your endpoint got rate limited. Code 500 means the server crashed mid-flight. Those 4 fail so early or so hard that the logging hook never fires. A 400 bad request or a 404, those still get logged. One more thing. If a request is bigger than 1 megabyte, it's saved as null, not dropped entirely. The exam tests this exact gap: 401, 403, 429, and 500. Time for another one. Question 8. Prioritize the stated requirement. A generative AI engineer at Callaway Financial is building an enterprise RAG application that must answer questions drawing from 2 data sources: a company wiki stored as PDF documents, and a live transactions database containing current account balances. How should the engineer architect the retrieval layer to handle both data sources correctly? Select 2. Review the answer choices on screen. The correct answers are option B and option C. Unstructured prose and live structured records need separate retrieval paths. PDF wiki content is unstructured text that benefits from embedding-based semantic retrieval via AI search, which can match user intent against passages even when query vocabulary differs from document vocabulary. Account balance data is structured, live, and time-sensitive. Feature serving exposes continuously updated values through a low-latency endpoint, ensuring balanced data is current at inference time rather than stale from a batch index. Converting transaction data to PDFs discards the structured relational nature of the data and introduces staleness, since re-export would need to happen continuously. Indexing all data together with BM25-only retrieval ignores the fundamentally different access patterns required. Semantic matching for prose content versus point lookup for structured records. A nightly snapshot would become stale immediately and is unsuitable for serving live account balances to customers. Ready. Question 9. Eliminate before you select. A generative AI engineer at Fenmore Bank is deploying an LLM-powered customer service assistant. The security team requires that customer SSNs, email addresses, and phone numbers never appear in model responses sent to downstream internal systems. They also require that any model response containing violent content be blocked entirely before delivery. Which 2 AI gateway guardrail configurations should the engineer enable? Select 2. Review the answer choices on screen. The correct answers are option A and option C. Replace and block modes are not interchangeable PII guardrails. Enabling PII detection with replace mode on model responses substitutes detected SSNs, email addresses, and phone numbers with anonymized placeholders before the response reaches downstream systems, ensuring that sensitive identifiers never appear verbatim in output. Enabling safety filters with block mode on model responses intercepts any generated content containing violent material and discards the entire response before delivery. Satisfying the hard block requirement. PII detection configured on model requests would scrub PII from the user's incoming message rather than from the model's reply, which does not address the requirement to sanitize outgoing responses. Rate limiting controls request volume and protects against cost overruns or SLA violations, but does not inspect or modify response content. Traffic splitting routes requests proportionally between endpoints for deployment strategies like canary releases and has no content filtering capability. Ready. Question 10. The scenario tells you the trade-off. A generative AI engineer is optimizing a RAG system for detailed technical documentation. Small chunks improve retrieval precision because they closely match user queries, but the LLM receives too little surrounding context and produces incomplete answers. Which architecture resolves this tension? Select one. Review the answer choices on screen. The correct answer is option C. Small chunks search. Large parent segments feed the model. Parent-child retrieval directly addresses the precision versus context trade-off. Small chunks of around 512 tokens are indexed for similarity search, ensuring that retrieved results closely match the user query. When those chunks are identified as relevant, the system retrieves their larger parent segments of around 2048 tokens to provide the LLM with rich surrounding context, improving generation quality without sacrificing retrieval precision. Using only large 2048 token chunks improves context, but reduces retrieval precision because large chunks contain multiple topics that dilute query matching. Semantic chunking groups content by topic similarity, which helps coherence but does not provide a mechanism to selectively serve larger context during generation. High overlap recursive splitting duplicates content at boundaries, but cannot independently serve a broader context window during generation while retaining precise retrieval granularity. Let's slow down here. The parent-child retrieval pattern is a classic exam trap worth understanding properly. Imagine you're searching a 500-page technical manual. You want the search to find the exact paragraph matching your question. That's precision. But the LLM reading the answer needs the full surrounding section. That's context. Those two needs fight each other when you pick one chunk size. Small chunks win the search. Big chunks win the reading. Parent-child retrieval gives you both. Index 512 token child chunks for precise search. When a child matches, pass its 2048 token parent to the LLM. The other options pick one side. Large fixed chunks lose precision. Semantic chunking can't serve two sizes at once. The trick: retrieval size and generation size don't have to match. Faithfulness targets context grounding, not topical relevance. Inference tables silently miss 401, 403, 429, and 500 responses. Parent-child architecture retrieves on small chunks but generates from large parent segments, resolving the precision versus context trade-off. Let us switch gears. Question 11. Identify the business need first. A generative AI engineer is comparing two revised prompt templates for a customer support chatbot. Both templates produce responses that independently score similarly on absolute quality scales, making it difficult to distinguish their relative performance. Which evaluation method is best suited for reliably identifying which template produces better responses when absolute scoring produces inconclusive results? Select one. Review the answer choices on screen. The correct answer is option C. Absolute scores plateau, relative judgment keeps working. Pairwise LLM-as-judge evaluation is specifically designed for situations where absolute scores are similar or noisy. Presenting two responses to the same prompt side by side and asking a judge which is better leverages the comparative nature of judgment, which is consistently more sensitive and reliable than independent absolute ratings when differences are small. Relative preference is easier to assess than assigning distinct absolute scores to two responses that are close in quality. NDCG is a ranked retrieval metric measuring the quality of document ordering in search results, not the quality of generated responses from a prompt template. Token-level perplexity reflects how predictable the generated text is to the base language model, which does not correlate with helpfulness, accuracy, or customer satisfaction. Human star rating panels can supplement automated evaluation but are expensive, slow to scale, and subject to inter-rater inconsistency. Pairwise LLM judging delivers the same comparative signal at a fraction of the cost and time. Let us switch gears. Question 12. Ignore details that do not change the decision. A generative AI engineer at Meadowbrook Legal is building a RAG system over thousands of lengthy regulatory documents. Users ask narrow, highly specific questions, but satisfactory answers require the surrounding legal context from a broader section to be fully understood. Which chunking architecture best satisfies both high retrieval precision and sufficient answer context? Select one. Review the answer choices on screen. The correct answer is option B. Legal answers need narrow search and wide generation context simultaneously. Parent-child retrieval indexes small child chunks for high-precision vector matching against narrow queries, while each child chunk is linked to its larger parent segment, which is returned to the LLM during generation. This architecture directly resolves the tension between retrieval precision and answer completeness. Narrow questions match specific child chunks, and the model receives the surrounding parent section needed for a legally sound response. Fixed size 1024 token chunks without overlap increase context per chunk, but reduce retrieval precision compared to smaller units, and the absence of overlap risks losing meaning at paragraph boundaries. Semantic chunking finds natural topic boundaries and improves coherence, but does not separately maintain different chunk granularities for search and generation, so it cannot simultaneously optimize both objectives. Using one chunk per full document eliminates retrieval precision entirely and forces every query to retrieve entire documents regardless of which specific section is relevant. Let us switch gears. This is question 13. A generative AI engineer at Conteso AI has been iterating on a text classification model, logging each run as a logged model in MLflow. After selecting the best performing run, they register it as a model version in Unity Catalog. What becomes available on the Unity Catalog model version page that was not visible in the experiment view alone? Select one. Review the answer choices on screen. The correct answer is option C. Promotion to UC consolidates performance history, not just renames. When a logged model is promoted to a Unity Catalog model version, all the performance data that was automatically captured during development, metrics, parameters, and traces, becomes visible and consolidated on the UC model version page. This provides a unified governance view of the model's quality history alongside its version metadata and deployment status. Raw training datasets are not automatically surfaced on the model version page through the logged model promotion workflow. External benchmark comparisons are not generated as part of model registration. Feature lineage connecting models to upstream delta tables requires separate feature store lineage configuration, and is not automatically included when registering a model from an MLflow run. Alright, question 14. Watch the exact wording. A generative AI engineer at Wingtip Publishing is building a legal research platform where retrieved documents are manually annotated with graded relevance scores: 0, irrelevant, 1, marginally relevant, 2, relevant, and 3, highly relevant. They want a single metric that rewards systems for both surfacing highly relevant documents and ranking them as high as possible in the result list. Which retrieval metric best meets this requirement? Select one. Review the answer choices on screen. The correct answer is option D. Graded labels plus position sensitivity demands a graded positional metric. DCG at 10, discounted cumulative gain at position 10, is the recommended retrieval metric for scenarios with graded relevance labels because it sums relevant scores across all retrieved positions while applying a logarithmic discount to lower ranked results. A document scored 3 appearing at rank 1 contributes far more than the same document appearing at rank 8, which directly rewards placing the most relevant items first. Recall at K counts how many of all known relevant documents appear in the top K results, treating every relevant document as equally important regardless of its relevance grade and ignoring where in the list it appears. Precision at K measures how many of the top K retrieved items are relevant, but treats all non-zero relevance labels as equivalent, discarding the granularity of the 0 to 3 scale. Mean reciprocal rank tracks only the position of the very first relevant result and discards all information about every other retrieved document. This one trips people up. Let's break down exactly why DCG at 10 beats the other 3. Imagine you're searching a legal database and you get back 10 documents. 3 are gold, 4 are useless, and the rest are somewhere in between. You want a metric that rewards both quality and position. Precision at K treats a barely relevant doc the same as your best one. It just counts non-zeros. Recall at K doesn't care if your top doc is at rank 1 or rank 10. MRR stops counting after the very first relevant result. Only DCG at 10 does both. It adds up actual grades and penalizes lower positions. A 3 at rank 1 scores about 3 times more than a 3 at rank 8. That's why, with a 0 to 3 scale, DCG at 10 is the only right answer. Alright. Question 15. Look for the constraint that matters. A generative AI engineer is evaluating the retrieval component of a customer support RAG system. The LLM only processes the top 3 retrieved documents in its context window, so a document ranked 4th or lower has no effect on response quality regardless of its relevance. Which retrieval metric should the engineer prioritize to measure whether the most relevant documents are placed highest in the ranked list? Select one. Review the answer choices on screen. The correct answer is option A. Top 3 cutoff makes rank 1 far more valuable than rank 3. NDCG, normalized discounted cumulative gain, at K measures ranking quality by applying a logarithmic discount to each retrieved document based on its position. Documents ranked lower receive less credit. A perfect NDCG at K score of 1.0 means the most relevant documents appear first, directly addressing the scenario where only the top 3 results are used for generation. Recall at K measures completeness of retrieval by counting how many relevant documents were found in the top K, but assigns equal credit to a document ranked first and one ranked last in those results, ignoring positional quality. Precision at K measures what fraction of returned documents are relevant, but also does not capture whether highly relevant documents are prioritized near the top. F1 at K balances recall and precision without accounting for ranking order. DCG scores graded relevance by position. NDCG normalizes against the perfect ranking. Registering a logged model as a UC model version in one step makes all captured performance history visible to stakeholders. Alright, let's read question 16. A generative AI engineer has been developing a fine-tuned summarization model and logging all experiments as MLflow 3 logged models, accumulating metrics, parameters, and execution traces across dozens of runs. The best candidate has been selected and the team needs to make the complete performance history visible to stakeholders through the Unity Catalog model version page. What single action accomplishes this? Select one. Review the answer choices on screen. The correct answer is option C. 4 plausible actions listed. Only one does both jobs. When a logged model is promoted to a Unity Catalog model version, all performance data captured during the development phase, metrics, parameters, and traces, becomes automatically visible on the UC model version page. This is the intended promotion path in MLflow 3, where the default registry URI is Databricks UC. Exporting runs to a Delta table duplicates data into a queryable format, but loses the structured model registry context and version governance that Unity Catalog provides. Duplicating the experiment to a shared workspace shares the raw run data, but does not create a versioned, governed model artifact in Unity Catalog. Changing the tracking URI only affects where future runs are logged and does not retroactively surface the existing logged model's performance data on the UC model version page. OK. Question 17. Map the scenario to the capability. A generative AI engineer at Pinnacle Commerce is launching a product recommendation assistant. During the pilot phase, the system receives approximately 60 queries per day from internal testers. 6 months later, the team plans a full customer rollout and forecasts 90,000 queries per day with strict latency SLAs. Which serving strategy should the engineer recommend for each phase? Select one. Review the answer choices on screen. The correct answer is option B. Traffic forecast and SLA requirements shift the serving tier calculus. Pay per token serving is the recommended choice for early stage or low volume workloads, because there is no capacity reservation and costs scale directly with actual usage. 60 queries per day does not justify reserving dedicated throughput capacity. Provisioned throughput is the recommended approach for all production workloads requiring consistent latency SLAs and high query volumes. At 90,000 queries per day with strict latency requirements, it provides the guaranteed capacity and predictable performance the production launch demands. Using provisioned throughput during the pilot wastes reserved capacity that sits largely idle at 60 queries per day, adding unnecessary cost before the system is proven. Pay per token does scale automatically, but does not provide the latency guarantees that strict SLAs require at high volumes and can become significantly more expensive than provisioned throughput when traffic is consistently high. OK. Question 18. This is a precision check. A generative AI engineer at Elmwood AI is building a document similarity search application using Databricks AI Search. The team requires cosine similarity ranking so results reflect semantic direction independent of vector magnitude. The engineer finds that Databricks AI Search uses L2 distance as its fixed underlying metric, and that no distance_metric parameter exists on create_delta_sync_index. What should the engineer do to achieve cosine similarity ranking within the existing infrastructure? Select one. Review the answer choices on screen. The correct answer is option B. The API won't let you pick cosine, but math will. Databricks AI Search uses L2 Euclidean distance as its fixed metric, and the similarity score is computed as 1 divided by 1 plus the squared L2 distance. For unit length vectors, the squared L2 distance equals 2 minus twice the cosine similarity, which means ranking by L2 distance and ranking by cosine similarity produce identical orderings when all vectors are normalized. The normalization must be applied consistently on both sides, document vectors at index time and query vectors at query time, for the equivalence to hold. Direct access indexes use the same L2 distance metric as delta sync indexes. No API parameter exists to switch to cosine distance on either index type, making this approach ineffective. Normalizing only query vectors while leaving stored vectors at varying magnitudes breaks the mathematical equivalence, producing L2 rankings that diverge from true cosine rankings. The RRF_param controls reciprocal rank fusion blending for hybrid search and has no effect on the underlying vector distance computation. This one hides a math trick, and the exam will absolutely test whether you catch it. Imagine 50,000 research papers as embeddings. You want to rank them by topic direction, not document length. That's what cosine similarity does. But Databricks AI search is locked to L2 distance, straight line distance between vectors, with no setting to change it. Here's the trick. Shrink every vector to length 1 first, then L2 gives the same ranking as cosine. Normalize every document embedding before inserting into delta, and normalize your query vector before calling similarity_search. Skip either side and the math breaks. Longer vectors skew results. A direct access index uses the same L2 metric. There's no config option there either. The exam rewards knowing you must normalize both sides. That's the trap. Here we go. Question 19. Follow the operational constraint. A generative AI engineer at Kestrel Analytics has been running a text summarization service on Databricks Foundation Model APIs using pay-per-token pricing for 6 months. The service now processes 50,000 summarization requests per day with a predictable, consistent traffic pattern during business hours. The platform team wants to reduce per-request latency variance and lower costs at this volume. Which change should the engineer make? Select one. Review the answer choices on screen. The correct answer is option C. Predictable traffic plus latency variance reduces to one answer. Provisioned throughput is the recommended configuration for production workloads with consistent, high-volume traffic. It allocates dedicated model capacity that eliminates the latency variance inherent in shared pay-per-token infrastructure and typically delivers a lower effective cost per token at sustained scale compared to on-demand pricing. The min_provisioned_throughput and max_provisioned_throughput parameters allow the engineer to right-size the allocation to the known traffic pattern. Pay per token is intended as the starting point for development and early-stage exploration, not for high-volume predictable production workloads. Routing through an external model via AI Gateway adds network hops and operational complexity without providing the dedicated capacity allocation that resolves latency variance at its root. Enabling inference tables adds monitoring visibility into request patterns, but does not modify the underlying serving configuration or address the infrastructure source of latency variance. Truncating prompts reduces per-call token counts, but degrades summarization quality and does not solve latency variance, which originates from shared infrastructure contention rather than from prompt length. Next up, question 20. Do not reward the familiar term. A generative AI engineer at Clearwater Financial has deployed an LLM-powered customer service endpoint via Databricks AI Gateway. The compliance team has 2 requirements: Social Security numbers and email addresses in both customer requests and model responses must be replaced with placeholder tokens rather than blocked outright, and the model must not generate hateful or violent language in its responses. Which 2 AI Gateway guardrail features should the engineer enable? Select 2. Review the answer choices on screen. The correct answers are option A and option C. Block versus replace. Compliance language specifies exactly which mode. PII detection and redaction replaces detected sensitive data such as social security numbers and email addresses with placeholder tokens in both the request and the response, satisfying the compliance requirement without blocking legitimate interactions entirely. Safety filters for hate speech and violence prevent the model from generating harmful language in its responses, meeting the second requirement directly. PII blocking is a distinct configuration that rejects the entire request or response when PII is detected, rather than replacing it with placeholders. This would disrupt customer service interactions that legitimately reference account details and does not meet the specification of replacement rather than blocking. Rate limiting controls request volume and prevents runaway costs but does not address content safety or PII exposure in any way. Traffic splitting routes proportions of requests to different model versions for gradual rollouts or A/B testing, and has no role in sanitizing PII or filtering harmful generated content. 3 takeaways from this session. First, FeatureSpec only recognizes feature lookup and feature function. Every other named component is a fabricated distractor. Second, provisioned throughput is the production default once traffic volume is consistent and latency SLAs exist. Third, unit normalizing all vectors before indexing makes L2 distance rank equivalently to cosine similarity in AI search. Know your 2 FeatureSpec components by elimination, provision before strict SLAs kick in, and normalize your vectors to get cosine behavior out of L2 infrastructure. Those 3 insights travel far.